this video, we're going to look at how to choose a technique to use to integrate, just focusing here on our A-B techniques. And it's going to be really important for us to understand how to make this choice as we start adding more techniques for integration to our toolbox. So for now, the techniques that we have, we can rewrite an integral. We can just apply the antiderivative rule. We can anti-differentiate. And when we integrate, ultimately, we're always going to do this technique. But sometimes we can do it right from the beginning. Sometimes sketching a graph is the best way to get the integral. Or we could use U substitution. And I've written these in this order. We have RAGU here, kind of a little mnemonic device to help us remember what our possibilities are. And as we learn new techniques, we'll add to this device to help us remember what our choices are. So let's look at, first of all, we're going to start with rewrite. And integrals that we need to rewrite, there's some different kinds. Whenever we have a radical, we know that we need to rewrite that as a fraction exponent. When we have x to a power other than 1 in our denominator, we need to rewrite that as a negative exponent. And sometimes we need to rewrite just using algebra, as in these last two examples. And this final example that I've written, I'm actually going to work this one for you. When we first look at this example, you might think U substitution, because I do have a function inside of a function. The problem with doing U substitution here, though, is that if I let this inside function be my U, then the du is 2x, and I don't have an x out here to cancel out. And so in this case, this is going to be better for us to square this out. X to the fourth minus 6x squared plus 9 dx. And now it's just a simple polynomial that we can easily integrate. So those are some examples for a rewrite. You may also have a trigonometric expression that needs to be rewritten, such as this one. And we know with our trig rules, there's only a few types of trig expressions that we can anti-derive. We have those on our list. And so here we're going to need to use identities to rewrite this. I'm going to rewrite my denominator, 1 minus cosine squared x. Hopefully we remember that's equal to sine squared x, because cosine squared plus sine squared equals 1. So now I have cosine x over sine squared x, which still does not match one of our rules. However, if I split up that denominator, actually, I'm going to write it a different way. Make it 1 over sine x times cosine x over sine x. So the sine squared x, I just made it sine x times sine x. 1 over sine x, of course, is cosecant x. Cosine x over sine x is cotangent x. And now this matches one of our rules, and we can anti-derive to get negative cosecant x plus c. Anti-differentiate, that was our second technique. I'm not going to do any examples of that. Those are just any function that matches one of the rules that we have from last year. Remember, we had 10 antiderivative rules that everything kind of comes back to. And so anytime we see any of those, we can just use a rule. But next I'm going to look at an example for graphing. And most of the time, a time when graphing is going to be really helpful is if you're doing a definite integral that involves an absolute value function. For example, the integral from 2 to 5 of the absolute value of x minus 2 dx. In this case, if we were going to try to just use antiderivative rules, we would have to rewrite this absolute value as a piecewise function of two linear functions because we don't have an antiderivative rule for an absolute value. So we would have to do it in pieces. However, if I just sketch a graph, This is the absolute value function. It's being shifted to the right 2 units. So we know that would look, my graph would look like this. I want to integrate from 2 to 5, which means I need the area from 2 to 5. And I can see that's going to be a triangle. This side down here would be 3. And this side over here, if I plug 5 into my function here, absolute value of 5 minus 2, that also equals 3. So this side is 3. And so this area is going to be 1/2 base times height, or 9/2. And so this integral simply equals 9/2. Finally, let's look at a quick example for u substitution. And I'm going to do an example similar to the first example I did for rewrite. But notice the difference here is that we are actually multiplying by the x. And so I can do u equal to x squared minus 3. My du is 2x dx. And so in this case, I have that x there to cancel this out. If we do it by solving for dx, then we get u squared times du over 2x, and my x's divide out, and I have 1/2 integral u squared du. 1/2 u cubed over 3, which is 1/6 x squared minus 3 cubed. Whoops, plus c. I forgot my plus c over here. Plus c there on the end. So having that x being multiplied out there, having that derivative that we can divide out, makes u substitution possible.